Okay, so today what we're going to do, a couple of things. What I wanted to first of all do is clarify a problem, an error that I had, at least in the notes I had jotted in the book, on a problem that we'd gone over where we had the hyperbolic functions involved. It was the impeller. So if you take a look on the overhead, or problem 146, here's the problem that we tackled the other day. And then my penciled notes here, I made the correction that we needed. The work we'd done on the board was correct. Where we got down, what happens is this particle, the water flows in and then it starts to move outward as it comes in contact with the fin. And as it moves outward, we're supposed to figure out what the acceleration's magnitude is just as it reaches the capital R radius. The capital R radius shown here. So right when it's on the outer edge here, what's the magnitude of the acceleration? So we went through the calculation with the hyperbolic function, and the radial acceleration turned out to be two terms which disappeared, went to zero. So there was no radial acceleration, there was only theta-directed acceleration. Since the impeller was spinning at a constant angular speed in rotation, then that means that the theta double dot term was zero. Can you folks see that up there? Yeah, reasonable. And then the only term, non-zero term then on the acceleration is the Coriolis effect. Coriolis effect. And that happens to be 2r dot theta dot, which mathematically was this term, which just tidied up by combining the kappa terms here into this expression. Now that's where I'd left the problem the other day, and it failed to look back at what we were supposed to actually figure out. It said in the question, figure out the total acceleration of the particle just prior to leaving the vane in terms of r naught, r, and kappa, just in terms of those parameters. So down here, we have this thing involving time. So the key to handling that is the fact that our initial R up here was given as a hyperbolic cosine function, which describes R, and we're letting R become capital R at the critical point. Everybody okay with that? So we're going to have a capital R here. So we have an expression then for the hyperbolic cosine of kappa t, which would be capital R divided by R naught. But we have hyperbolic sine in our acceleration expression, so what we needed to do is use an identity for hyperbolic functions, that the square of the hyperbolic cosine minus the square of the hyperbolic sine is equal to 1. So what we could do then is we could solve this for the hyperbolic sine, which mathematically turns into this, where we're going to place that as a capital R right there, and then tidy that up a little bit, and then here's the final answer right here.
Could you zoom that in?
Oh, zoom in a little more? Sure. See that? So down there at the very, very last step. Should I go through just the bit of algebra needed to kick this into that? Anybody need to see that? Sometimes people have trouble with radicals and this thing turned into this. Why don't I go ahead and do that on the board here? So we have that the acceleration on the right over there is twice the initial radius, kappa squared, times hyperbolic sine of kappa t. What we're doing is coming in here and replacing this expression with the radical because our initial r was given to us as r naught hyperbolic cosine of kappa t, and at capital R, capital R over r naught then is going to be the replacement for the hyperbolic cosine expression. And what we needed is this identity is 1. And so the hyperbolic sine expression here kicking it over to the other side and bringing the 1 back over is this hyperbolic cosine squared minus 1. And we put in this right here. So we have r squared over r naught squared minus 1, which is the square of the hyperbolic sine. And then, if we chose to, we could write that as r squared with a common denominator like this, right? And then put that in, the radical of this in, right in here. And so we have twice r naught kappa squared, and replacing this hyperbolic sine with the square root of that expression. We have r squared minus r naught squared. Taking the square root of the denominator, r naught comes out and reduces out here to yield the answer, which should be 2 kappa squared times the radical. So I would encourage you to not do some of these steps in your head. Just write them out so you don't miss a term or a constant. Okay, so that clarifies something from last class session. Okay. A reminder to mark your calendars for Tuesday the 28th of April, 5:30 to 7. We'll have guest speakers, and they'll be over in room 161 in the math area from OSU, talking about the transition to upper division. Okay. How many of you would be able to attend that? I need to see approximately head count. 1, 2, 3, 4, 5, 6, 7. What about the rest? 8? Rest of you? Can't do it? Okay. It would be worth your while because they'll give you the inside scoop on what to look out for. You can ask them questions about professors that you may or may not want to take, that kind of thing. So that's always important. Okay. All right. So today, let's answer any questions you may have, probably about polar questions. And then I'd like to move into space curvilinear motion today. A couple people have come up and asked questions about some of the assigned homework on polar problems, and some of you may not have gotten to me to be able to help you out with that stuff. So is anybody puzzled on any of the problems? I could give you a little bit of insight to get you on the right track. Yeah.
Yeah, there was one. I'm looking for it right now, but
Let's see, 151 was assigned, 155 was assigned.
I think this was one from the normal tangential.
Okay, back a little further.
Yeah.
Okay.
Okay, it's number 137 actually.
Okay, we're going to pull that up here. It must be polar. Yeah. 137?
Yeah. Oh, okay. magnitude of the velocity. That was pretty straightforward. And then I had all the pieces of the acceleration, you know, to use the formula. And then it ended up not agreeing with what the book has.
Okay. So what we have is we have a block that is on this shaft that's threaded. It's a radially controlled slot with a power screw. And for the instant represented, this angle theta, so this arm is rotating. It's in rotation. Here's angle theta defined. It's rotating at 1/10 of a radian per second. And it's got some deceleration. So what does that mean that's physically happening?
It's being pulled clockwise a little bit.
Well, it's turning which way? Counterclockwise or clockwise?
Yeah, clockwise, but at a
Hold-
decreasing rate.
Hold it.
Turning counterclockwise.
It's turning counterclockwise.
Right,
Because it's a
velocity's
positive, it's a
but it's slowing
positive
down.
radians per second. And here's your defined angle theta down here. So the angle is opening at 1/10 of a radian per second.
Okay.
It's opening at 1/10 of a radian per second, moving counterclockwise, and it's, as you mentioned, it's slowing down at 4/10 of a radian per second squared, when the radius is 300 millimeters. So we also notice that because of the power screw here, it is moving physically, the pin is moving physically outward at the same time the rotation of the arm is happening. It's moving physically outward at 40 millimeters a second. At this instant, determine the magnitude of the velocity and acceleration, and then sketch those if the angle theta is 120 degrees. How many of you have finished that problem?
That same thing as
Okay.
him, though.
Just two of you. Okay. So let's go ahead and spend a few minutes on it, just because this problem might give us a little bit of clarity as far as places that might help you with some of the other problems. Okay? Grab an eraser. So we have the arm with a pin in there, and it's at a theta angle at this instant of 120 degrees. It is moving radially outward with an R dot reading of 40 millimeters a second. At the same time, the angle, we have a theta dot, which I believe was positive 1/10 of a radian per second in its rotational rate, and theta double dot was a negative 4/10 of a radian per second squared. So it's rotating counterclockwise and at the same time slowing down while it's moving radially outward at the same instant. The question was asking, for that instant, determine the magnitude of the velocity and the acceleration at P, of point P, and then sketch the vectors when theta is 120 degrees. So we want the magnitude of the velocity, we want the magnitude of the acceleration, and we want the velocity vectors and the acceleration vectors sketched when theta is 120 degrees. There's a sort of concise statement of all the given information in the problem. How many of you feel like you have the velocity equation in your head in polar without having to look it up? Nobody, huh? Okay. And that means then you don't have the acceleration in your head either. Okay. So what I'm trying to get you to the point of doing is being able to have a sense of what's occurring in polar. So if you have some object on some radius with an r hat and a defined theta, setting theta hat typically in this kind of a situation, then what I want you to be thinking about to be able to get a handle on that is the fact that it might have a telescoping kind of an effect on velocity, and it's got a pseudo-rotational kind of a term going on, which you're familiar with from circular motion, should be an r omega kind of a term, or an r theta dot. And those are your two components in polar for your velocity. Now, if you're going to do the acceleration and try to remember it, then you want to think, okay, this radial telescoping term could be changing with time, so there could be a telescoping effect, accelerating it outward or inward. So you should expect that. And if it's on some curved path, you know there's also has to be a term directed back towards the center of curvature, or it's a pseudo-normal term because the path may not be directly circular to this or perpendicular to this arm here. So it may not be that, but there's going to be another term pointing back this way, which is one that you've seen earlier, r theta dot squared or a v squared over rho. And actually, that's going to be a v squared over r in this condition, in this situation, because this is the term that's pointing back towards the pole. So the combination of that telescoping effect outward and this pseudo kind of normal term pointing back towards the pole, the addition of this minus this is going to be that radial one. Did that help you remember this stuff a little bit? Okay. Now, the thing could be speeding up in its rotation about this pole. So there could be an r alpha type of term, which is going to be an r theta double dot type of term. And then you also have to think that there is a term when you're moving radially, when you're in motion radially on a rotating body. I mentioned this last week, and you'll hear me say it again several times, this term. If you're moving radially on a rotating body, there's going to be this other term called the Coriolis term. And that points in this direction, in the same direction as this positive sense of r theta double dot. So you're going to have a 2r dot theta dot term also pointing that way. So your polar acceleration equation then is made up of your radial one, r double dot, minus your r theta dot squared term, r hat, plus the r theta double dot, plus the Coriolis term, 2r dot theta dot. And that has to be in the theta hat direction. Back here on the velocity, these two components yield your velocity vector, being r dot in the r hat direction plus your r theta dot in the theta hat direction. I wanted to make sure we went back over this before we get into this problem, and also because if we start looking at three-dimensional motion, we're going to want to use these things again in one of the conventions for describing 3D type of motion. Any questions on that? Okay. So now, all the stuff we need to do this problem is probably summarized right there. So, here's an r dot term, here's a theta dot term, and what's the prescribed radius at this instant on this power screw? 300 millimeters? Okay. And everything is in millimeters in our units, so I think we can just stick with that for determining our velocities and accelerations. Okay. Now what I would probably do is work up the vector expressions first, and then this would be elementary to figure out the magnitudes once you know those. So let's go ahead and do that. So our velocity, if you look here, we've got our r dot. We know r and we know theta dot, so we've got our complete vector velocity. So the r dot's 40 r hat plus our 300 for the r, and the theta dot is a tenth theta hat. And so the vector velocity is going to be 40 r hat plus 30 theta hat. Units, millimeters per second. Okay. If theta is 120 degrees, I've drawn that somewhat accurately here, then I can come up here and go ahead and lay those two components of velocity onto this sketch. So then up here, I would have a 40r, that's going to be that direction, and I'm going to have 30, trying to relative to scale here, 30. So the true velocity then, vector, would be pointing this way, the diagonal. Mm-hmm.
Is that the velocity that we'd see if we were sitting? No, okay, never mind. I was going to ask if that's the velocity that we'd see if we were sitting at the pole, on the pole. Then no, we wouldn't see any of the theta velocity because we rotated with it. Okay, so never mind.
No, this actually is the true velocity. It doesn't matter where you're sitting. As a matter of fact, you could put a mask. Imagine that you had a curtain in front of this whole mechanism. You couldn't see the screw, power screw, but all you could see is maybe this is a little light behind the curtain shining up on the curtain, and you just watch this particle, watch this light, little spot of light move. And it would be following a path. As this thing moved radially outward, it would be in rotation, so it would be following a path, maybe looking something like this as it went. Does that make sense? Okay, yeah. As a matter of fact, we could, if we wanted to spend more time on this, we could actually work up the path, say assuming this thing started with the arm pointing over to the right and with the pin right here at the origin, following these prescribed values as this thing moved. Except what we'd have is we'd have to deal with the deceleration. We'd have to have some other information about how that would progress. You've seen some other problems where you've actually had the description of the path, where r was described as a function of time, theta was described as a function of time, and you can actually use your graphing calculator in parametric mode and work up the equations to actually see that path followed. Okay. Well, back to this. So there's a sketch of theta. Of velocity. The magnitude. Let's go ahead and wrap that up. The magnitude then at this instant would be what? Which is 50 millimeters per second. See, textbook problem. 3, 4, 5 kind of thing. 3, 4, 5 kind of relationship. Textbooks have those kind of things in them all the time. Yes?
So how do we know, though, that r hat is always perpendicular to theta hat?
We derived that last week.
Okay, sorry, I missed some classes. So
Okay. Well, we have DVDs that you get to watch. Okay. It's better than Netflix. Okay. So what you can do is we actually derived why r hat or why theta hat is always perpendicular to r hat.
r is the radius of curvature at that point. Right?
No, r is actually a distance coming off the pole. So it's physically the distance from a defined pole, and that unit vector, this unit vector called r hat, always points outward from that pole, and it goes with the particle. And then perpendicular to it, in the sense of increasing theta, perpendicular to r hat is always the unit vector theta hat. And those go with the particle as it's in motion. Okay. So then the speed here is going to be the square root of the sum of the squares of the legs, which is going to be 50 millimeters per second at that instant. Okay? The acceleration then, did they tell us that r dot was constant?
Yeah, so there would be no acceleration.
Yes. So that's a constant. So therefore, this implies r dot constant implies that r double dot is then 0. So to work up the AR, the radial acceleration term, r double dot is 0. And so we subtract r theta dot squared from that, and that's going to be our 300. And our theta dot is a 10th being squared. And so our AR term is going to be, this is 0.01. So that's going to be -3. And this is going to be in millimeters per second squared as an intermediate result. Did you have that okay, Jake?
Yeah,
Okay.
yeah.
The next part there.
The next part, the A
It
theta.
just screws everything up. It goes.
Okay, so A theta is defined as r theta double dot plus the Coriolis term. So we drop in the given information, and we have a deceleration on the theta at -4/10 plus 2 r dot was 40. Theta dot was a 10th. So there's 8 right there. And this one right here is 40% of 300 is 120, -120. And the sum of those for A theta is -112 millimeters per second as an intermediate result.
Squared.
Thank you. Millimeters per second squared.